So we've been talking in this, from the algorithm's point of view, we've been talking about how we would come up with an algorithm to solve a given problem. And to use a computer to solve a given problem, it makes sense to have the solution come out in a timely manner, right? Not have it take 70-something years like we talked about last class. So when we look at problems that we've classified, the original attempt was to classify problems as being exponential complete, meaning the best algorithm anybody could ever come up with to solve the problem would take exponential time, and therefore it doesn't make sense to use a computer to solve the problem that way. So we've come up with this class called NP-complete, which many computer scientists believe is equivalent to exponential complete. And as far as, up till recently, those algorithms cannot be solved by a polynomial time algorithm. So it starts to make sense that if we happen to have a problem that is NP-complete, or like we talked about, an NP-hard, so I'll get to that in a second. So let's say, for example, this is a problem that we have shown to be NP-complete. This is actually NP-hard. This is the Knapsack problem. We talked about this problem earlier in the course when we were talking about dynamic programming. But the problem was, if you're given a set of items, each of the items has a weight to them, and each of the items has a value to them. And then you're given this one big knapsack, which can hold up to, let's say, big W of weight. The idea is to try to fill the bag with as much value as possible. So you have a weight capacity that you can't go over, and you want to put as much value into the bag as you can. So if you remember, we were talking about if you could do fractions of these items. If you could say, I want 4.5 of one item, and then the remainder of other items. If we could do fractional parts, then we could solve this problem very easily. We find the item with the biggest value per weight, and then put as many as that in until the bag is full. But if you remember, we went over the example, if you can't do fractions of the pieces, then you had leftover parts, and maybe if you went the greedy approach, getting the thing with the most value, you might leave some room that was wasted, and we could have done it better another way. So it turns out this kind of seems to the eye like an easy problem to do, but if you think about it, the weight could be any number, could be millions. And the number of items we could use could go into the millions too. So the computational complexity, as it stands right now for that famous knapsack problem, is it's NP-hard. So if you remember the difference between being some class complete and some class hard, complete means someone has demonstrated that the problem can be solved with an algorithm that is in that class. And it also it was proven that it could never be done in something better than that class. That would be whatever the class is, complete. If something is proven to be some class hard, that means a solution to this problem would solve other problems that are complete for that class, but this one may not even be in this class. It might be even harder than that class. So a better name might have been harder with an ER on the end. If it said NP harder, or NP possibly harder, something like that, would have probably been, I don't know if there is a right way to say this, but this problem is as hard as NP-complete problems and possibly harder. That's what the NP-hard means. So if we wanted to solve this problem, we'd realize writing a computer program to do it would be, I'm not going to say pointless, but it would take such an incredible amount of time. We'd probably never end up seeing the results for it. So now what we want to do is come up with something that's pretty close, an approximation algorithm. So all approximation algorithms are algorithms that go to solve a problem, but accept the fact that we might not get the best answer, but we're hoping to get something close to the best answer. So if you're ever asked to come up with an approximation algorithm for a problem, You're not trying to solve it, you're trying to get an answer close to the optimal algorithm, but the efficiency of your algorithm is so much better than getting the correct answer that it becomes worth it. So in the 1980s, 1990s, probably up to the late 90s, if you went, and I'll bring up Amazon.com, we'll look at a few books on approximation algorithms, and it's almost always they're solving problems that are NP hard. But recently, approximation algorithms for polynomial problems even starts to make sense, because there's polynomial algorithms that will take maybe a few minutes to run, and now with the internet and people wanting results faster, even those algorithms are considered no good, so you have to find approximation algorithms that are better than the algorithms that are already known. So whenever you're asked to solve and to come up with an approximation algorithm for the problem, you're not necessarily solving the problem, you're coming up with a solution that's pretty close to the best answer. And the reason you're doing this is because the running time of your approximation algorithm is acceptable and the running time of the real algorithm is unacceptable. That's the only reason you'd be doing it. So for an example of an approximation algorithm for the knapsack problem would be, this would be kind of like if we could do get partial credits for items, but we can sort all the items based on a value divided by weight order. So if something's worth $10 but only weighs 5 pounds, that's considered a gain of 2, let's say. And if something else was worth $16 but the weight was 9, that would be worth less to us. So then we try to get as many of the items that have the best value divided by weight, get as many of those in, and then in the remaining room pick the next one that could possibly fit and push as many of those in. As we talked about earlier in the course, that would not give the best answer, but it would give a pretty close answer. And then you could argue that it would fill up at least W over 2 of the bag, because obviously we would keep pushing the items in until there wasn't enough room for another one. And then we'd fill up at least half the bag. But again, it's not the greatest it's not going to get the best algorithm. It's not the algorithm that gets the best answer, but it's one of many approximation algorithms for it. I just want to go over some simple examples here. Okay, so now I wanted to, this is just kind of a side conversation back on the idea of NP completeness, but we left off in a previous class, we said that the vertex cover problem was NP complete. So let me talk about two similar problems, and we're just going to make an argument that these two similar problems are also NP complete. So the vertex cover problem, if you remember, we had a graph might be simple enough to make the point. We said that this was a vertex cover. This was a minimal vertex cover. Because those 2 points, if we label these A, B, C, and D, B and C would be a minimum vertex cover for this graph. With those 2 points, every edge got picked up at least once. So that was a minimum vertex cover. There's another question, so that's the vertex cover question. Then there's a question of, so that would be find the minimum vertex cover problem. Suppose there was a question asking for the maximum independent set. That would be, given a graph, find the maximum number of points that you could pull out of the graph, and using that as a subset, none of those points touch each other. So we'll pick out a group of points. So for example, you couldn't say A and C are part of an independent set because A and C touch each other. They're connected.
They represent an edge, in other words.
There's an edge between them. So like if you said my independent set, well, let's see, so the vertex, the minimum vertex cover would be B and C. That would be a minimum vertex cover for this graph, G, right? Now, if I ask what's the maximum independent set, you can't put in the answer, we're gonna put some points in here. You can't put in 2 points if there's an edge between them. So, if you, actually you can't put, if you put C in, you can't put A or B or D.
A and D.
Yeah, A, right, it would be, A and D do not touch each other. Right, anything else, B and C actually touch everything, so B and, once we put B or C in the answer, we can't put any other thing else. So, now what is the correlation between the minimum vertex cover of a graph and the maximum independent set of a graph? It's almost, they're a lot more similar than meets the eye.
But if you looked at the set of, they're what's left over, if you will, or, they're.
Yeah, so actually,
if you took out the minimum vertex cover.
if you took those points
set,
out, what
and
property
you're left
do the remaining points have? They couldn't be touching, there couldn't be an edge between them, because if there was an edge between them, if you have a graph G and you pull out a subset of the points that constitute a vertex cover, that means every edge came out with it. Like, let's say you pulled out the points and all their edges with them. All those edges would come out with them. If there was any points left that had an edge between them, then your original vertex cover was not a vertex cover. You missed something. So, and as soon as you can find the minimum vertex cover of a graph, you have also found the maximum independent set, because whatever was left over has to be an independent set. And if you found the minimum vertex cover, then the remaining points are the maximum independent set. So, the argument we went over last class went something like this. If somebody could come up with a solution for the vertex cover problem that could run in polynomial time, then we could do this. We could say the original NP-complete problem was convert the SAT problem to 3 conjunctive normal form SAT. That would be, so that would be, we'd be following these steps where we take any size clause and make it its comparable 3 conjunctive normal form clause. That we could do in linear time. Then we would feed that into, so I'm kind of drawing an algorithm, and this takes linear time. Step 1 takes linear time. So after that step is done, we do a second step. We convert the 3 conjunctive normal form SAT problem to a graph that feeds into the vertex cover problem. Remember, what we did was for every clause we made a triangle, and for every literal we made a bar, and then we linked the triangles to the bars and then asked ourselves, could we find a vertex cover of size 2 times the number of triangles plus 1 times the number of bars? And if we could, that circuit was satisfied. And if this circuit was satisfiable, then this circuit was satisfiable. So then we would feed this into a solver for the vertex cover. Solver. This algorithm, this entire algorithm, if I drew a box around the whole thing, this would solve the original problem, which is the SAT problem. We take a circuit that has random terms to it, doesn't have to be three conjunctive normal form, any random circuit. We run it through a converter that converts it into its equivalent three conjunctive normal form circuit. And actually it turns out if two conjunctive normal form can be solved at polynomial time, but three and higher cannot. So we take a random circuit, we convert it into its equivalent three conjunctive normal form circuit, then convert that into that corresponding graph, and then feed it into something that can solve the vertex cover problem. This takes linear time, this takes linear time. We haven't looked for a solution to this, so we don't know how much time that one takes, but one thing we do know is the overall algorithm for SAT, this is circuit satisfiability, this is NP complete. This is actually, what do we call this, Cook's theorem. And this is Cook's theorem. From 1971. And the theorem is that the satisfiability problem is NP complete. So it can't be solved in polynomial time. But we're looking at a solution for it right now. Step one, convert the circuit into a three conjunctive normal form circuit. That can be done in linear time. Step two, convert the three conjunctive normal form circuit to a vertex cover graph. And then step three, run this thing, however long this takes. So what do we know about this? If this could be solved in polynomial time, linear or n squared or n cubed, the whole thing can be solved in polynomial time, and according to Cook's theorem, that's not possible. So therefore, there is no polynomial time solution for this problem. So then this one becomes an NP complete problem. But now it looks like with this independent set, if someone could come up with a solution for the independent set problem, we could do this. We could say, what would we have, what is the conversion?
The extraction from the overall set of edges.
Well, we would reverse all the edges, right? And then, yeah, because if 2 points are independent, so if in this case, the edges don't have direction and the edges don't have values on it. It's just a connection. For 2 points to be independent of each other in one graph, if we computed its complement, that would be everywhere there's an edge, remove the edge, and everywhere there's not an edge, add an edge. They would be connected. So any 2 points that are independent would become connected, and any 2 points that were connected would then become independent. So we can convert a graph asking a question about the vertex cover into a graph where we're asking what's the biggest independent set by just, well, I guess if we could, well, yeah, we could do it that way. So we could just reverse all the edges, so we could convert G to an independent set problem. And then the fourth step would be to solve. Now this one, to convert a graph to its complementary graph would take how much time? For every for every combination of points, we'd have to ask ourselves, is there an edge there? And if so, take it away, and if not, add it. So that would be v times v minus 1. We would have to look if there's an edge and then remove it or not. So that would be v squared.
I mean, Java has I guess, a set interface, right? And if you use sets, just mathematically, if I thought about it that way.
Yeah, there might be something better than v, well, we could definitely do it in v squared, right? For every pair of vertices, ask ourselves, is there an edge? And if so, remove it, and if not, add it.
Well, walking through a set of edges. A set of edges, if you stored a set of edges, that's, oh, I think.
So, yeah, I mean, but either way, this definitely can be done in polynomial time, right? Whether it's v squared or maybe going through, it might be able to be done in linear time, but definitely in v squared time. And then feed that into a solver for the independent set. A solver that can tell us what's the biggest independent set in the graph. So this can be done in linear time, this can be done in linear time, this could be polynomial, maybe even linear. And then this fourth step would actually solve the first ever NP-complete problem. So these can be done in polynomial or better time. So what does that tell us about a solver for the independent set? It can exist in polynomial time. If it did, Cook's theorem is wrong. So now we have another example of a problem that cannot be solved in polynomial time. And as long as we can keep, this was kind of like the argument we made where we said if somebody proved you cannot drive from New York to Paris, and then if somebody proved you can drive from New York to Miami, that means you now can't drive from Miami to Paris, because if you could, then the original statement that you couldn't drive from New York to Paris becomes false.
So we're saying Cook's theorem is inviolate. In other words, that's the gold standard.
Yeah, so that, right, so the original Cook's theorem, what he basically tried to come up with was a problem that could never be solved in anything short of exponential time. And then using that problem, start to find similar ones that also could not be solved in anything less than exponential time. And then they kind of came up with this other class, NP, which is almost exponential, and a lot of people think it is exactly the same class as exponential. But if this is, the gold standard, if this problem could never be solved in less than, well, this class NP, then any other problem that could be used to solve it or something like it could then also has to be NP complete. Yeah.
So it raises the question in my mind, the idea of the max independent set, of can you use that if you find the max independent set? It's an approximation, but is there a way of relating that back somehow to determine how good your vertex cover, minimum vertex cover approximation was?
Well, so now there's a correlation between this one and then a third problem I just have up on this slide. There's a question of a clique. There's a problem, so if, let's say, let me just define what a clique is, and then I'll go back to this slide. Suppose there was a graph that had A, B, C, and D. A clique would be a collection of points where every point in the set connects to every other point. So a clique is like, sometimes you might hear a clique as a group of friends that are very close to each other, something like this. So I'll draw a 4-point clique. That's a clique, so it's 4 points where every point is touching every other point, and then I'll add a few more points just to have like a non-clique graph. Okay, so a graph like this, if you were asked the question, what is the maximum clique in the graph? The maximum group of points where they all touch each other, it would end up being these 4 points. I kind of drew a clique in the middle and then I threw some more points around it. But those 4 points would be the maximum clique. So we have 3 graph problems that are somewhat similar to each other. One is the one we talked about earlier, the vertex cover. And now we have these two other ones. One is the so let's see, we have the original vertex cover problem. Given a graph and some number k less than the vertices, we're looking for a subset. Does the graph have a vertex cover of size k or less? That is there a subset of vertices that for all edges, at least one of the endpoints of u and v are covered in the vertex cover of the graph? Then the Clique problem is, given a graph and a positive number k, which is a subset of the vertices, does the graph contain a subset such that every two vertices in the set are joined by an edge in the original graph? So Clique is a group of points that are all completely touching each other. They're all connected to each other. It's not just a connected component. So if you said A, B, and C are a clique, that means A is connected to B, B is connected to C, C is connected to A. And then the independent set, which is kind of a negation of that, would be, is there a subset of vertices within the graph such that none of them have an edge between them? So the question of what is the maximum independent set, it's obviously easy to find a minimum independent set, just find 2 points that are not touching each other and you found a 2-point minimum independent, a 2-point independent set. But if you were given a graph and said find the maximum set of points that are have no connection between each other, that ends up being an NP-complete problem. And the reason we just walked through was if you could solve the independent set problem, you could then use that solver to solve a vertex cover problem. So the connection between these three problems, the vertex cover, the independent set, and the Clique equivalence, is basically saying if you have a graph, anytime you have a graph, if you have a subset of the vertices, V prime, the following statements are equivalent. If V prime is a vertex cover of the graph, then all the points, not including the V prime ones, all the other points must be an independent set. Otherwise your vertex cover wasn't correct. And then all the points minus the ones in your vertex cover is a clique of the complement of the graph. The complement would be if you took away edges that are there and put edges that are back. So if there's an edge between 2 points, take the edge away. And so consequently, the inputs of these three problems can all be converted into each other in polynomial time. So that means if you found a solution to one of these three problems that could run in polynomial time, you could convert the input of one to the other and then solve the other problem in polynomial time. But as we were stringing all those steps across, when we were coming up with an algorithm, we started to realize we could solve Cook's original problem. The random circuit is a random circuit satisfiable. We could solve that problem in polynomial time if we can solve any one of these three in polynomial time. So if we could solve any one of these three in polynomial time, we can solve all three of them in polynomial time, and then using any one of those, we could solve Cook's original problem in polynomial time. So if you ever found a solution for any one of these three in polynomial time, this whole topic of NP-complete problems could all then be solved in polynomial time. Really, if you solved one of them, you could solve all of them in polynomial time. So to this day, nobody solved any problem that's known as NP-complete. So that leads us to the idea of if you were given a graph and asked to find a vertex cover, if the number of vertices, as we talked about earlier, got up to be 15 or 20 or so, it could take years for your algorithm to finish. So you'd want to start looking for approximation algorithms. So one example, let's see, this makes sense. So we have a set C, which starts off as empty, and then we have a set called E prime, which takes all the edges of the original graph. While that set is not empty, pick out an arbitrary edge and add that edge, so C is going to be like our answer set. This would be, we're trying to find not the minimum vertex cover, but a pretty low number of vertices in a vertex cover. we add that edge to our answer, and then we remove from E any edge that is connected to U or B. And then we return C. So does it make sense what this is doing? It's not necessarily going to give the best answer, but we randomly pick out an edge. So let's say there are 2 points A and B. There's an edge between them. We pick an edge A, we pick the edge between A and B. We take that out, and then we say anything connected to A or B, throw those points away because they're now covered. I'm sorry, throw those edges away because they're now covered by the fact that we picked out A and B. And then do that again, and every time we pull one out, throw away anything we've covered.
And you can do that off of an adjacency linked list.
Right. Now it might seem a little wasteful because usually if there's an edge between A and B, if we put both points A and B into our answer, the edge between them was covered twice, right? And we only have to cover every edge once. But this way we cover it twice and then we get rid of a lot of edges. So there might be a better answer than this, but it's somewhat good. And it almost makes me think, why don't we just pick a point and throw away all the edges connected to it, then pick a point.
Interesting.
That might actually might give you a better answer, but that would run V.
The problem going down to the end to me was, what you went over last week, as soon as you run in, you can do it in a very straightforward fashion, I believe, until you get to the situation when you found the vertex covers on initially. The question is, are there any triangles? If there are, you got a problem, I believe. Finding the triangles is a separate issue.
Okay.
And then the question is, do you try to find the triangles first and deal with them, or after? And
wait, what problem is this with the triangles?
wait, remember a problem you did on the board the other day, the last time we were here?
Yeah.
You had one up there, and it was easy to see the first set. Well, every place, when I looked at it, every place there was a triangle.
Right.
That's where you had a difficulty. And if you tried to identify them, if you try to identify the triangles, because
right.
you had to cover, every time there's a triangle, just picking how we started, picking the largest, picking a node which had the greatest number of edges coming off of it.
Right.
Right?
Okay.
That's
yeah, so we were using a greedy method.
Right, the greedy
method. We've taken that one, then
right.
We said all those edges we can get rid of.
Right.
Yeah, and then that caused us, the ones around it ended up being the right answer, not that one, and then that forced the ones around us to leave our answer, and then that caused ones that were sparse to have to get forced into the answer. Yeah. Right. But yeah, it was still kind of a good.
When I looked at it, you were left with the triangles, and that was the
right.
That was the trick.
Right. So that would be another approximation algorithm, which we talked about last class, where we would take all the vertices and sort them by the count of edges that come into them, and then just grab try to get the most. Every time we pick a point, we want to cover as many edges as we can. But that doesn't guarantee the best answer. That could force us to then pick points we can't use anymore.
This is number 4.
This is what?
This is our number 4, right?
For the homework? Yeah, so there's a number of answers to, there's a number of ways to get this, and yet there will be the only algorithm that will get you the right answer for any graph in the world is the exponential algorithm of try every permutation of points, count up, and try every permutation of points that cover try every permutation of points. Ask yourself, does this cover all the edges? If so, remember that as the small, and then keep the smallest one you found so far. So yeah, this is kind of another answer for that question. And then at this point, you're trying to argue, like in a worst case scenario, how far off could this be from the original answer? And this one will be at least what's the best way to phrase this? At least,
75 years.
well, no, that would be in time. No, this one will run, the running time of this approximation algorithm is order E, is that right?
I'm talking about the exponential.
Yeah,
version.
that could run forever.
75 years off from this.
But this one will run order E, because all we're doing is for every edge, we grab an edge, then look on our, assuming we had an appropriate data structure, assuming we had a linked list to represent the graphs, not a grid. We grab an edge, and then for every edge connected to it, we remove those edges. So it's just walking along that linked list.
Interesting.
Then grab another one, remove all those. So the whole algorithm should run order E, and in the absolute worst case scenario, we could end up with a vertex covered twice as big as the perfect answer, the ideal answer. Because every time we grab an edge, we're adding both points to the answer. It's possible we could have gotten away with just adding one of them. Obviously, for every edge, one of the 2 points has to be in our vertex cover answer. But we might be adding double the points. That would be like, for you to come up with a graph that had that property, that using this algorithm, you double the approximate answer, it would be like lightning striking, not twice, but V times. But it's possible to come up with a graph where, using this algorithm, you'd come up with double the answer of the optimal answer. But this looks like a pretty good answer. And then if we went over last class, if you try to pick something better than just a random, this is just picking an arbitrary edge. If we picked, instead of an arbitrary edge, if we picked a vertex with the most edges covered, a greedy one, that would probably do better than this.
And then if you, what I tried was you continued, after you removed that, you've taken care of that.
Right.
You went something similar to that. You then pick whatever's left out of, you pick the next, you become greedy again. You keep.
Right, that's what we'd always do. We try to be greedy again,
right,
at the next one with the most edges for our pick. But yeah, that could force us to then have no choice but to pick up a bunch of points that don't give us much.
Will you eventually clean out there's a way that you can eventually clean out the adjacency list.
Okay.
I mean, that's what I think.
Right, so in this case, for example, there is obviously an exponential algorithm to solve this, and that would be take every permutation, every subset of all the vertices, and then ask yourself, step one, is this a vertex cover? So check off every edge, make sure every edge is covered. If so, what is its value? And if its value is better than all the values we've found so far, then save this as the best answer. And try that for every permutation of the input. So that's an exponential algorithm that will definitely give you the correct answer, but that could take years and years to do. And then this is a linear time algorithm that gives you an answer that's pretty close. But you have to know it's not the best answer. Okay, so now that we have an approximation, anytime you have an approximation for an algorithm that can just be converted directly to another problem, we now have an approximation algorithm for the clique problem. So the algorithm for the maximum clique is compute the complementary graph. That means everywhere you see an edge, take one away. Everywhere there's no edge, add an edge. Then run the algorithm we just showed on the previous slide. Find the approximation algorithm for the minimum vertex cover problem. And then return the original set of vertices minus the ones the algorithm just gave us and say those must be the maximum clique. That's because these problems are all like, in other words, an approximation algorithm for any one of these three could be used to do an approximation algorithm for the other ones, just like any solution to these could be used to solve the other one. So then another, probably one of the most famous NP hard problems is an algorithm where you have a bunch of vertices. All the vertices are connected to each other, and they have values on the edges, what the distance between them are. and you're asked the question, can you travel around the graph in such a way that you visit every city exactly once and do it in the shortest amount of time? So they call it the traveling salesman problem. So if you're like a salesman who has to go to New York and Chicago and San Francisco, and you have to hit every city at least once, and you want to do it cheapest, the cheapest way of traveling, what's the quickest way to hit all cities at least once? So this problem can be shown to be NP hard, because if somebody could come up with a solution for this one, they could then use that as a solver for the problem where, no, not the Clique. There's a problem called the Hamiltonian cycle. The person named Hamilton came up with this. But that's where you have a bunch of vertices and all the edges between them. The edges between them they don't have lengths on them. There's just, they're either connected or not connected. And you're asked the question, can you create what's called a Hamiltonian circuit, and that's where you visit every vertex exactly once and form a cycle in it. And so that seems like a much easier problem than this, and in fact it is, but even that one is NP complete. Because we could show that you could make these little subgraphs where you link them together, and that you could create these little subgraph widgets and link them together and ask yourself, is there a vertex cover that could cover all these points? And if so, then the original graph had a Hamiltonian cycle in it. So this question, if this question was solvable, then this question could be converted, a solution for this one could solve the Hamiltonian cycle one, because the Hamiltonian cycle is a graph where the distance between the cities are either 0 or 1. And in the traveling salesman problem, the distances between cities can be any number. But the other one is just, if there's an edge between them, it's a 1, and if there's no edge, the distance is, the distance would be infinity or 1. And even that problem is NP complete. So this problem would be a solver for that one, and this one ends up being, in the class, called NP hard. So it would not make sense. At first you might think, hey, I think I can come up with an algorithm for it. I'd start at one city and go to the city that's closest to me. Right? It's kind of a greedy algorithm. And then from that one, take of the n-2 remaining cities, go to the one closest to me. But that could cause you to go down a path where then you have, your final city is, you have to go all the way back across the country, and it might have been nicer to not do that. Like you could go, from New York to Philadelphia, and then from Philadelphia to Chicago, but maybe Washington, D.C. you skipped because you kept finding something closer and closer, which then took you away from one of the cities, and you have to come all the way across the country back for the one you missed. So a greedy algorithm wouldn't work here, and it turns out that this is also an NP-complete problem. So once you know a problem is NP-complete, it makes sense to go looking for an approximation algorithm for it. So one such approximation algorithm for the traveling salesman problem would be to select a root, or one of the vertices, call that the root vertice, and then from that root create a minimum spanning tree of all your points. This we know we could do using Kruskal's algorithm or Prim's algorithm. Kruskal's algorithm, if you remember, looked at all the edges and sorted them from smallest to biggest and started adding the smallest edge as long as you didn't make a cycle. Prim's algorithm said focus on one point and then add anything you can connect to it, taking the smallest one, and also don't make a cycle. So if we follow Prim's algorithm, we pick a point like a starting point, follow Prim's algorithm, and build a minimum spanning tree. That we know we can do in, I forgot what the running time of Prim's algorithm, but it was something like v log v plus e, or it was obviously something polynomial, something that can be done very quickly. And then then take that answer, that minimum spanning tree, and just visit all the nodes in a pre-ordered walk through them. So that would be, if you remember, a pre-ordered walk was, if you had a tree structure, you would visit the left child, then the parent, and then the right child, following that pattern. Oh, no, sorry, no, that would be in order. Pre-order would be the left child, the right child, and then the parent. Parent always comes after. And then that would give us, that would make sure we visited every point at least once, and we'd follow that path. It's not necessarily the best path, but if you have a minimum spanning tree and you start visiting all the nodes, most of the nodes, not all of them, will be close to the one you're currently at. Oh, I do have the run time here. So, okay, so it looks like Prim's algorithm, the topological sort, the pre-order walk should take V plus E. And that's the V plus E here. So the Prim's algorithm was V plus E log V. And then just returning the graph at the end once we're done. The graph of all the points that we visited. So what this algorithm is basically doing is, by creating a minimum spanning tree, you're connecting a bunch of points that are near each other, but there might be some long links between them. And that's really the downside of the algorithm, that it won't give the perfect answer. But it tries to group all the cities kind of near each other, so when you're in one area of the country, you hit as many in that area as you can. But if you remember, a minimum spanning tree could have a group of points here and a group of points here, and then one big arc connecting them. And then there might be another big arc that comes back to where the other ones were. So it won't give the best answer, but it'll cause us to hit a bunch of cities near each other, maybe take a long hop, hit a bunch of cities near each other. And in a bad case, we'd take a hop kind of back to where we were before. That could happen on a minimum spanning tree, which would not be the ideal answer.